So here, let's talk more about the solution region and what it actually is, all right? And because what the solution region is going to help us do when we start talking about linear programming is going to define where our possible answers are, right? And in a solution region, the solution region can be one of two things. It can either be bounded by the lines or it can be unbounded by the lines. The points that fall on the line are what we call our boundary lines. All right. And each point where the intersections occur between the two lines is called a corner point. And the corner points are going to do something special for us when we get to linear programming. And we'll talk about that when we get to that actual area. But because the graph can be bounded, the word bounded means that when I look at a solution region, if a solution region is bounded, that means I can draw a circle around the region and encapsulate it. If it's unbounded, that means that when I draw this circle here, it keeps going on forever. So this is a bounded region right here. Notice that you get a polygon out of that bounded region actually. And this is an unbounded region here. And notice that you can't draw the circle around it there. So we're going to go through some particular examples and we're going to see if we have bounded regions or unbounded regions. And I want to identify corner points. Corner points are intersections. So when we look at this, here's how we typically set up some kind of linear programming problem. And in particular, you'll notice you have these right here, right there. And we'll talk about those later, but these are what we call non-negative restraints. They're called non-negative restraints because in business, what it means is that you have to make a product. And it's going to talk about products and making products and maximizing or minimizing profit. Because we have to make a product, X and Y are going to be our products. We have to make those. We're always going to be put in the first quadrant. So what that means is you're always going to graph every one of these lines in quadrant one. That's what this is saying, graph in quadrant one. And that's why you only have positive quadrants right here, by the way, the positive quadrant. So when we graph this, let's graph the first line, which is 2x plus y is less than or equal to 22. So 2x plus y less than or equal to 22. And when I do that, I'm going to get y by itself. So to get y by itself, I'm going to subtract off 2x. So I get y is less than or equal to negative 2x plus 22. And to plot that, that's just a intercept of 22. Slope says go down 2 over 1. So I'm going to go down 2 over 1. And notice I'm getting this line right here. Like this. And it's a solid line there. It's going to be a solid line there. So we're going to draw in a solid line. I'm going to try to make this line as straight as possible here. So we get this line right here, first off. Let's draw it in. Here's your first line. And the shading on this is as shade below that line. So we're shading below the line. That means we're going to shading where the y's are getting smaller or below the y-intercept. So that's shade inside of here. That's your first line. The next line is x plus y is greater than 13. Or it's less than or equal to 13, I'm sorry. So we get y by itself. Y is less than or equal to, move the x over, becomes negative x plus 13. So I'm going to plot 13 on my intercept. Go down 1 over 1. We get this line right here. And this line says shade below it again. So we're going to shade below this line like this. And then the last line says 2x plus 5y is less than 50. Two x plus 5y is less than or equal to 50. So again, get y by itself. This time I'll subtract off 2x. So that's a negative 2x. And that's plus 50. And I'll divide everything by 5. And I get y less than or equal to negative 2/5 x plus 10. So here I'm going to plot 10 first. This time the slope says go down by 2 over by 5. Here's the line I'm getting now for this. This one says shade below that line as well. So here, what I've created now, I'm looking for that overlap, and I can see that the overlap is occurring from here, from here, to here, to there. There's my overlap. And if I want corner points now, I want to identify the corner points. I'm looking for the intersections of lines. Remember that this is also a overlap part. This is the equation y is greater than 0, and this is the equation x is greater than 0. So that's also overlap. So I'm being bounded by these corners. Here, 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 and here. At every one of those points, we have an intersection. This point as well. So we have the point 0, 0. We have the point, it looks like 0, 10. We have the point 5, 8. We have the point 9, 9, 4. And we have the point 11, 0. Here are all the corner points that are given in this particular problem. There are all the corner points. Notice here that this region is bounded. It's bounded. You can draw a circle around this. This is a bounded region. And when a particular region is bounded, what you're trying to do there is you're trying to maximize your profit. You want to maximize things when it's bounded. And so here what we're trying to do is we're going to maximize the value in the terms of a linear programming problem when we get there. So here's another example where we try to identify corner points by graphing. So again, what we're going to do first is we're going to try to get these equations to y equals. So I have 5x plus y is greater than or equal to 22. And notice here on this equation, when I do this, get y by itself. So I get y, move the 5x over there, it's greater than or equal to negative 5x plus 22. And so when I plot that point, I'm going to plot 22 on the y, on the x, on the y first, and then I'm going to go down 5 over 1. So down 5 over 1, down 5 over 1, down 5 over 1, down 5 over 1. And then I'm going to go down further than over 1. I get something like this. So I get a line that's doing something like a very steep line here, by the way. It does something like that. So here's your first line. Next line says x plus y is greater than or equal to 12, right? And so y is greater than or equal to negative x plus 12. Down 1 over 1. And you want to try to make your lines as straight as possible, although mine are very good. But I'm seeing that that's going to be another corner when I look at this because they're intersecting here. Oh, and I should go back to this purple one. This purple one says shade greater than. So the purple one says shade up here. The red also says shade greater than. So you're greater than the x-intercept. Greater than the y-intercept, I'm sorry. Like this. And then another one, I have a green one, which says x plus 3y is greater than or equal to 18. So move x over. 3y is greater than or equal to negative x plus 8 plus divide plus 18. Divide everything by 3. Y is greater than or equal to negative 1/3 x plus 6. So down 1 over 3. Down 1 over 3. Down 1 over 3. There goes another corner. Down 1 over 3. Down 1 over 3. Down 1. Down 1 over 3. And so here goes another line that I've created. And I'm above that line as well. So if you notice this right here, We're above that line. And because you're above that line, notice that this region goes on forever. The solution region is going on forever. As a matter of fact, it's everything. Your actual intersections occur here now. From here to here to here. Where you're bounded by this point right here at 0, 22. You're bounded at this point right here, 3, 9. This point here, 9, 3. And this point down here, 18, 0. And because the bounding is not, because you can't draw a circle around this because it goes on forever, this is what we call an unbounded region. This is what we call an unbounded region. And so in a problem where it's unbounded, what you're trying to do is, we're going to talk about this in linear programming, but what you're trying to do is minimize this. You want to minimize loss in a particular problem like this, or minimize cost.